This is a movie about the energy of orbital motion. So you're familiar with some possibilities for orbital motion. There's, of course, the elliptical orbit, in which the less massive body orbits the more massive body in an elliptical orbit, and the more massive body is at one of the foci of the ellipse. And then the circular orbit is a special case of the elliptical orbit, where the more massive body is at the center of the circle. In either case, the energy of the mechanical energy of the satellite is equal to its kinetic energy plus its potential energy. We know that the kinetic energy is 1/2 mv squared, and we've derived that the potential energy is minus gmm over r. In this equation, little m stands for the mass of the satellite, and big M stands for the mass of the body that's being orbited. So let's take an example, the special case of the circle. So if the satellite is orbiting in a circular orbit, we know that this is the energy. And we've also derived in the past the orbital velocity for an object that's in a circular orbit. I'm just going to review that quickly. So we start with F net equals mass times acceleration. And remember that the force acting on the satellite is a gravitational force. It's equal to gmm over r squared. And on the right-hand side of the equation, we know that the acceleration is v squared over r, so we can make that substitution. And then with a little algebra, you can solve for v to get the orbital velocity, and that's equal to the square root of gm over r. So this expression can be substituted in for v, and with again, a little bit of algebra, you find that E is equal to 1/2 gmm over r minus gmm over r. And simplifying that expression a bit, you find that E is equal to minus gmm over 2r. So this is the mechanical energy for a satellite that's in circular orbit. Okay, so what happens if we change things a little bit and we have an elliptical orbit? Well, it's beyond the scope of this course to derive this equation, but it turns out that the mechanical energy for an elliptical orbit looks very much like the mechanical energy for a circular orbit. Simply substitute in A for R, and you have the mechanical energy for an elliptical orbit. And just as a reminder, 2A is the major axis of the ellipse for the orbit. So now what I'd like to do is show you a specific example to show you how this expression can be used. And so the example is there's a massive planet or something, and there's an object that's going to be orbiting in an elliptical orbit. The radius of the planet is r, and what we're interested in knowing is, okay, if this object starts with initial velocity vi and makes it halfway through the orbit, what will be the height above the planet at that position, or the maximum height above the planet? And if you draw another radius in this direction, you can see pretty clearly that the maximum height is going to be equal to 2a minus 2r. So using our expression for mechanical energy, E equals k plus u, we can substitute on the left-hand side for E minus gmm over 2a. And on the right-hand side, we can substitute the expression for k plus u. Now, at any point on the ellipse, there will be a velocity, and the radius from the center of the planet can be measured, and so you can make substitutions. What the substitution we're going to make is going to be for the point we described, where the satellite is being projected from a point that's right near the surface of the more massive body. So I'm going to substitute vi for v in that expression on the right-hand side, and r for the radius. And you can imagine that you might know the mass of the planet, you might know the radius and the initial velocity, and at that point you should be able to solve for 2a, which you can then substitute into this expression, and then you can find the maximum height that the satellite reaches.